In previous discussions, we talked about what happens when you have a capacitor attached to a battery. And we remembered that when it is attached to that battery, no matter what the capacitance is in this sort of setup, that the potential difference across the plates is going to just be the same as the potential from the battery itself. So in that case, we know what this script E is supposed to be for the battery, what that potential difference across is supposed to be, and so we know it should be the same then across the capacitor here. Now, if we want to apply Kirchhoff's law to this sort of setup here, and if we imagine we were going along in the direction of the current we would imagine from the battery, the way we'd write that then is we'd have the potential difference across the battery, and that'd be positives if we're going in the direction of the battery. We are supposed to then go across the capacitor, and what potential difference is across that. And we know this all has to sum up to 0. So this one way we can easily see that indeed the potential across the capacitor needs to be the opposite potential then from what the battery is, just to make sure that that all nicely sums up to 0 here. Now this of course was assuming a system with no resistors. If we were to add that, our equation is going to get a little bit more complicated. So I have now reset up the same sort of circuit here, but this time I've included a resistor, and we'll still think about the current going and doing the rules for Kirchhoff's law in this way. We'll do the simple loop rule, and we'll try to write down what the equation ought to be. So again, this battery has some sort of potential across it, so we use script E to represent that, and so we'll have E. We have current going over this resistor, resistance R, minus IR. And then we have the capacitor and what potential is across that. The potential across the capacitor, put sub C there just to specify that. All this sums to 0. Now we also remember from the definition of capacitance that it is defined as the charge on the capacitor divided by the potential difference across that capacitor. So I'm going to do that to substitute into this equation. And we'll give myself a little bit of space to do that. So now rewriting this, we have the potential of the battery minus the potential drop over the resistor. And now we include the charge on the capacitor at some time divided by the capacitance itself equals 0. Now, this equation might be a little bit harder to solve, and there's also one other feature you may notice. Here we have charge, and here we have current. And remember that current has a certain definition as well. Current is defined as the change in charge over time, or basically the movement of charge. So these are charges that are actually, moving about. Well, if we have charge here, and we have change in charge here, we actually have ourselves a differential equation. So this means that we're actually going to have something ultimately that's going to depend on time, since the variable that's ultimately changing here is the time variable describing the charge across. So we need to try to set this up as a differential equation and try solving that. So you'd want to get all the charges on the left side of the equation, everything not charged on the right side of the equation, so that way you can try to take the integrals of both sides. The solution you're going to get will have the following form. We work it out and we can find that the charge on the capacitor, as we'll use a little q for that, and it will be a function of time, is going to equal the capacitance, the potential on that battery, times 1 minus e to the minus t divided by RC. RC then that being the resistance of that resistor there, and C the capacitance again. So this tells us how the charge is going to be building up on the capacitor, but to some sort of limit. So we can see that if t gets very large, then e to that factor, that minus factor, gets very, very small. So 1 minus something very small becomes basically just 1. So eventually the capacitor charges up to some maximum amount, depending on its capacitance and the potential due to our battery. And if we want to, we could also divide both sides by that C. And if we did that, if we divided both sides by the capacitance here, we'd have Q divided by capacitance. And if we remember from the previous equation, we know how that relates to the potential again. So we'd actually find that the potential difference between the plates as a function of time would be the potential from the battery, 1 minus E minus T over RC. And again, so this would say that there'd be some maximum potential on the capacitor. In this case, again, due to the battery's maximum amount, which makes sense. If the resistor weren't there at all, if R were 0, then it would just become this part of the equation here. It would just become the battery again. So that much makes sense. There's also, we could try describing not just the charge, but we could also describe what's going on through the circuit in general and ask what's the current through the system here. Again, since we know that current is the time derivative of charge, it's how much charge is moving through at a certain amount of time. So if we take the derivative of both sides of this equation, take the derivative with respect to time, we're going to find then that the current as a function of time is going to equal the battery's potential again divided by R, E minus T over RC. And so we actually see another interesting thing is that the current will start at some maximum value. When T equals 0, then you have E to the 0, which is just 1. So initially, the current is just the resistor, just dependent on the resistor and how much potential is from the battery, as if the capacitor weren't there at all. But with time, this value is going to get smaller and smaller. It's going to go from a maximum value of 1 at time 0 to something very, very small as time gets very big. And so eventually the current will stop. The capacitor will reach the same potential as the battery, and it'll be like two batteries pointing against each other, the currents that they would produce, and it would just cancel everything out. So that's what this will describe here with the current. It will slowly die off on us until the capacitor is at full charge. For simplicity also, the factor of RC here, we also tend to give it its own little definition. We represent it with a lowercase tau, and we call that the time constant. What the time constant will represent is how long it basically takes the battery to have charged up or charged down a certain amount. And that in particular amount is when it's e to the minus 1 power, which is around 62%, somewhere in that range. So this becomes a useful thing when you're doing any sort of analysis with exponential growth and decay. So after this much time, RC, you will have lost maybe or gained 66% of the charge in your battery or your circuit, or this much potential on the capacitor. All of the setup we've done so far is when we're thinking about charging a capacitor, but similar principles should come into play if we're discharging a capacitor, if we already had a capacitor with some potential across it, some charge on it, and then we let it flow through some sort of resistor as well. So let's try drawing that and see what Kirchhoff's law would produce. The form of it is going to look almost identical to what we had before. There's just no script E in this equation to represent the battery. But we still have a differential equation to solve ultimately. So we're going to get very similar results to what we did before, but it's going to have some significant differences. One thing that you might guess is how the potential isn't going to grow across the capacitor as it did before when it was charging, but we would expect, if anything, the potential to shrink with time. So if we try solving the differential equation we have here, it's going to have the following result. So we'll make a little bit of space to give that, and that result, again, doing the same sort of procedure as described in your book if you want to follow all the steps, but the solution is that the charge on the capacitor will still be a function of time. It'll be that maximum Q that we had on there, e to the minus t over RC. So with this expression, you can see that the charge will slowly dissipate off the capacitor and eventually reach no net charge on those plates anymore. And if we then, of course, also use the same definition of capacitance, we can see then how the potential across that capacitor is going to be a function of time, and it'll start with whatever the initial our initial potential across it was, whatever. I'm going to call that script E naught just to represent that. And it'll still have the same equation form, so the potential will slowly drop until it goes to nothing once time gets very large. And if we also take the time derivative of our first equation here, as we did before, we find that the current through our system here is also still going to be a decay function. We find this form, the same sort of exponential form we saw before of e to the minus t over rc, or minus t divided by tau if we want to use the time constant instead. But again, the current will slowly die off, which again makes sense. If the charge on the capacitor is shrinking, then there should be less current than it could possibly pump through this circuit. And it also means that what's going to happen is how this all depends on the size of the resistor. If the resistor is very, very, very large, then we will see how there's actually a very slow change in things. And if the capacitor is very, very large, it'll be a slow change in things. Now, having a very large capacitor, doing that makes sense. There's a lot of charge it can have build up on there, so it would take a while for it to all completely dissipate. But why would a large resistor make it the current go through there last longer? Consider also if R is very large, then the current in general is going to actually be quite small. This is going to be the current initially here, so when time equals 0, this will be the current. So if R is very big, then the current traveling through is very small. And if it's a very small current, then it's a rather small potential drop over that resistor, since delta V equals IR, as you'll remember from our definition. Delta V equals IR. So because there's such a small potential drop due to being such a huge resistor, there will be a very small amount of current, but the current value will stay constant or close to that same amount but for a longer period of time. All from what can be described from these equations, ultimately based on Kirchhoff's law and solving a differential equation.